Swayam Prabha. Digital India. Educated India.
Okay, welcome back to this lecture of laminar and turbulent flow. We have left the last lecture before introducing the topic of shear stresses in turbulent flow. So, we are going to continue with this particular topic. So, shear stress in turbulent flow. We are going to talk about a model that is called Bosnes model, where the total shear stress in case of laminar flow, it was due to the viscosity, viscous. Sorry, that was only due to the viscous. But in a turbulent flow, there is an additional component of shear stress that happens because of the turbulence in the flow. So, therefore, the shear stress in total is much larger than the viscous flow. At least it is definitely larger than the viscous flow, because there is shear stress that is associated with turbulence too. So, Bosnes says as T viscous is mu du dr for laminar flow, therefore, the shear stress due to the turbulence component is eta du by dy. Here you see this is similar. So, instead of mu there is something called eta, a new coefficient of viscosity, okay, and this is called eddy viscosity. So, we are not going to the derivation right now. At some point we can see these derivations when the appropriate chapter comes, but now you have to take that the shear stress due to turbulence is eddy viscosity du by dy, very similar to the shear stress in the laminar flow. The coefficient is therefore different, okay. And if we want to write a kinematic eddy viscosity, then we write it by epsilon, for example. So, this can be written as eta by rho, similar type of definition as laminar flow. What is eta for laminar flow, for example, or mu for laminar flow, that you already know. We have been doing that. It was 10 to the power minus 3 Pascal second. No, okay. So, eta for laminar flow will be 0, yes. So, but mu for this laminar flow is 10 to the power minus 3 Pascal second, and if the flow is laminar, eta is going to be 0 because it is related to the turbulent viscosity. So, unlike the dynamic viscosity mu and kinematic viscosity nu, eta and epsilon are not fluid properties. They are not fluid properties, okay. The values of eta and epsilon are dependent on the flow conditions. So, epsilon decreases towards the wall, becoming 0 at the wall. So, the epsilon, that is the kinematic eddy viscosity, decreases as you move towards the wall and becomes 0 at the wall. Now, coming to what is Reynolds shear stress. So, Reynolds in 1886 gave expressions for turbulent shear stress between two fluid layers separated by a small distance, and he said that the shear stress due to turbulence can be written as minus rho u prime v prime whole bar. Actually, it is not an assumption, but this can actually be derived, which we will do at some point in this hydraulic engineering course, but not now. So, you have to understand Reynolds shear stress is given by minus rho mu dash v dash, and it does not have only one component, it has minus u dash w dash, it will have minus v dash w dash. So, there there are different, there are some normal shear stress, but this is one of the shear stress component. Whereas what is u prime? That is the fluctuating velocity component in x direction. V prime is fluctuating component of velocity in y direction. Experiments show that u prime v prime is usually a negative quantity. Therefore, the tau turbulence or minus rho u prime v prime whole bar is total or positive quantity. It has negative correlation, that we will see. Now, there is a concept of Prandtl's mixing length theory. So, turbulence shear stress can be calculated if this thing is known, u prime v prime whole bar is known, because as we see the tau turbulence by Reynolds was given by minus rho u prime v prime whole bar. So, what a nice thing it would be if we can calculate u prime v prime bar, because that is unknown until now. Okay. So, accurate determination of u prime v prime whole bar is very difficult. Therefore, in 1925 Prandtl introduced the concept of mixing length, which can be utilized to express the shear stress here in terms of some measurable quantity. Okay. So, mixing length Lm, he said it can be described in terms of mixing length Lm. He said mixing length Lm is the distance between two fluid layers in the vertical direction, in the y direction, such that the bundles of fluid particles from one layer could reach the other layer and mix in the new layer in such a way that the momentum of the particle along the flow direction is the same. So, he related it to mixing, okay, and he said that the mixing length is the distance between two fluid layers in the vertical direction, okay, such that the bundles of fluid particles from one layer could reach the other layer and the mixing can happen, okay, something like this. So, this is the velocity profile, and he says he divided the fluids into layers, and this he says is the mixing length, okay. All right, we are going to explore this in more detail in the next slide. So, Prandtl related u prime to mixing length Lm. He said that this u prime, as you can see in the figure here, he said proportional to u prime, but I am going to write it on the next slide. He related u prime to the mixing length Lm as, he said this u prime can be written as mixing length Lm multiplied by the gradient of the average velocity. Okay, so he said u prime, this is very important to know, Lm as du bar by dy. This is what his assumption was, where v prime is also of the same order of magnitude as u bar, and similarly this can also be written as v prime is equal to Lm du bar by dy, similar type of equation, okay. And if you substitute equation 11 and equation 12 in Reynolds stress model, which was, it was tau turbulent is equal to minus u prime v prime whole bar, you get, so minus minus will become positive, it will become tau turbulence is rho Lm square du by dy square. You can just substitute and see, Lm du bar by dy multiplied by Lm du by dy bar, okay, is the same thing. So, it becomes rho Lm square du bar by dy. This is equation 13. So, this is one of the, this is the mixing length theory of the Prandtl. So, Prandtl also assumed that the mixing length Lm is a linear function of distance y from the wall or any solid boundary. Therefore, he said Lm can be written as ky. So, if you go back and see here, now rho is known, du by dy can be calculated because we are dealing in terms of average velocity, right, which can be measured. Now the only unknown is Lm. So how do we find this Lm now? So the problem is becoming less and less complex. We are going from one variable to the other. Now the only unknown thing is Lm. So Prandtl needed to relate this to something. So he assumed that Lm is a linear function of distance y, and he said Lm is equal to kappa into y, where kappa is known as van Karman constant and it has been found to be equal to 0.4. So he said mixing length is 0.4 times y. This is quite an important result. Okay. So now we know everything. For example, right, shear stress in turbulent flow was related in terms of u prime v prime, which was made by Prandtl, as u prime and v prime are of the same order of magnitude and is equal to which was proportional to du dy Lm, right, and Lm is equal to kappa into y. So now we will see the turbulent flow in pipes now. So in turbulent flow, the viscous shear stresses exist only near the boundary. So, and most of the region is dominated by the turbulence. So near the boundary, the viscous shear stress will act, and that are the only places where its existence. Hence the total shear stress can be approximately obtained from equation 13, okay, as the total, this was equation 13, correct. So we call this now equation 15, but because most of the shear stress in turbulent flow is due to the turbulent shear stress, so we can neglect the viscous shear stress. We say tau is equal to rho Lm square du by dy whole square, where u is the time averaged velocity. The over bar on u has been dropped just for simplicity. Okay, so if we use equation 14 in equation 15, what was equation 14? Lm was kappa into y. This was what we said in equation number 14. Okay, so we can simply write rho k kappa y whole square into du by dy whole square, correct, or we can simply write du by dy is 1 by kappa y divided by tau by rho, and this is equation number 16. Very simple. So for small values of y, it can be assumed. So if the y is very small, we can assume that tau is equal to tau naught, where tau naught is the shear stress at the pipe wall and can be assumed to be a constant. So at the wall, the shear stress is assumed to be constant and equal to tau naught. Okay. And therefore, what we can say, if we substitute tau is equal to tau naught in equation 16, we can obtain du by dy is equal to 1 by kappa y in the root T naught by rho, or du by dy, this quantity actually tau naught can be written as rho. So, but the catch here is, what is the catch? We have considered less small value of y, correct. So du by dy can be written as 1 by kappa y, and under root tau by rho is rho u star, so it becomes 1 by kappa y u star, and this u star under root tau naught by rho is the shear velocity, and this has the dimension of velocity. And if you integrate the equation number 17, so what we can get is simple integration. It will get u star by kappa, y will be ln y plus a constant c. This is very simple integration from here to here. You can attempt it. Okay. Then using the boundary conditions. What are the boundary conditions? So u at y is equal to r, where r is the radius of the pipe, okay, we will get u is equal to u max. Alright, that is what we have seen. At the center line of the pipe, the velocity is going to be the maximum. Okay. So, if we use this boundary condition, u at y is equal to r is u max, we can get u is equal to, we put u max here, okay, y will be r, and therefore we can obtain c. Okay. C will be u max minus u star by k ln kappa ln r, and if we substitute this as C, then we can get equation u is equal to u max plus u star by kappa ln y minus ln r, or u is equal to u max plus u star by kappa ln y by r. Okay. Or if when we substitute kappa is 0.4, we can get u is equal to u max plus 2.5 u star ln y by r, and this is equation number 20. This is just simple manipulation, and as you can see, we have derived a logarithmic velocity profile starting with the Prandtl mixing length theory for turbulent fluid flow. Okay. So, laminar flow was something like this, okay, a parabolic profile. Here a profile is little different, u is u maximum plus a logarithmic profile. So, it looks like something like this. Okay. Now, the equation 20, this equation 20 can be expressed as u max. So, what we do is we bring u on the other side. Okay. So, we bring u on this side and we take this whole side component this side. Then what we result is u max minus u, because u max will always be larger than u, is equal to 2.5 u star ln r by y, y will always be less than r. Or we bring u frictional velocity down, then we get u max, you bring it down here by dividing, then you get u max minus u by u star is equal to 2.5 ln r by y, and so this is ln, correct. So, we can put it in form of log. This is simple manipulation. We can get u max minus u by u star is equal to 5.75 log to the base 10 r by y. Okay. U max minus u is called the velocity defect or velocity defect law. Okay, this is velocity defect law. This is just simple, manipulation of these terms here. Okay. So, now we are going to solve one of the problems, problem number 7. And what it says is the velocity of water. So, what we have learned in this particular lecture is about the turbulent flow, and this problem 7 will help you in solving any problem that is based on this particular concept. So, it says the velocities of water through a pipe of diameter 10 centimeter are 4 meters per second and 3.5 meters per second at the center of the pipe and 2 centimeters from the pipe center, okay, respectively. Considering turbulent flow in pipe, determine the shear stress at the wall. So, we need to determine tau naught. Okay. So, let us see how are we going to solve this problem. We are going to have a white screen first. As always, what we do, we solve, we write given diameter is given as 10 centimeter. Try to always write down in SI units. Okay, so we write 0.1 meter. So diameter is 10, so radius is going to be 0.05 meter. Okay, u max is given as 4 meters per second. that is at y is equal to r, correct? And this is also given, u at r is equal to 2 centimeter is given 3.5 meters per second, that is y is equal to r minus r. So, y is going to be 5 minus 2 is equal to 3 centimeter, alright. So, u at y is equal to 3 is equal to 3.5 meters per second. So, alright. So, now u max, we are using the minus u by u star was 5.75 5 log r by y, okay. So, substituting the values here, this from here, this equation 4 minus 3.5 divided by u star is equal to 5.75 log base 10 5 by 3. This will give us u star as 0.392 meters per second. We also know u star is under root tau naught by rho, or tau naught is rho u star whole square. Therefore, tau naught, rho is 1000 and u star we already got, sorry, 0.392 0.392 whole square. So, tau naught is coming out to be 153.6 Newton per meter square. This is the solution to the question that we have at hand. All right. So, going back again to the slide. So, what we got was approximately 153 Newton per meter square, the shear stress at the wall. Okay. So, now the turbulent velocity profile is much fuller compared to the parabolic profile of laminar flow case. Okay. So, actually this is the flow, this is the true picture, this is the laminar flow that we have seen before, but below is, this is the V average and the velocity fluctuates or deviates from these depending upon the flow condition. So, this is the V average line. Okay. There are several other layers, viscous sublayer, buffer layer, overlap layer and turbulent layer. So, as I told you in the last slide, there are different layers in turbulent flow, and we are going to talk about that. Turbulent flow along a wall consists of 4 regions. Okay. Viscous sublayer, this layer is this layer next to the wall. So, this is the closest to the wall, where the viscous effects are dominant and the velocity profile is almost linear. Okay. So, in viscous sublayer the viscous effects are dominant and the velocity profile is linear. In the buffer layer, though turbulent effects are becoming significant, the viscous effects are still dominating. Okay. In the overlap layer, the turbulent effects are much more significant but still not dominant. Okay. In the overlap layer, in the turbulent layer, the turbulent effects dominate over these viscous effects. Now, when it comes to these beds and these regimes Some of the important terms that are there is hydrodynamically rough and smooth boundaries. Okay. So, this is the, if you see, there is a term called K, okay, here if in here. So, K here is the mean height of the surface irregularities. We talked in the beginning that the turbulence could occur due to the presence of irregularities on the surface. So, let us say the mean height of the surface irregularities is K, and delta dash, for example, is the height of viscous or laminar sublayer. The first layer that we talked, the viscous sublayer, okay, that was where the velocity profile was almost linear. Okay. So, outside the laminar sublayer, the flow is turbulent. That is what we have talked about. Eddies present in the turbulent zone try to penetrate the laminar sublayer and interact with the boundary. Okay. But when the surface irregularities are much smaller than delta dash, the height of the viscous sublayer, the eddies are unable to reach the surface irregularities. Okay. When the roughness height is much less. Therefore, we define that boundary as a smooth boundary. So, smooth boundary are the one where the thickness of the viscous sublayer is much larger than the surface irregularities. We will see what those surface irregularities here represented by K. When K is much larger than the delta dash, that is the thickness of viscous sublayer, the irregularities are above the laminar sublayer, leading to the interaction of eddies with the surface irregularities, and therefore these are called rough boundaries. From Nicoratz's roughness, K by delta dash, if it is less than 0.25. So, these values which we are going to talk about has been derived from experiments by Nicoratz. Nicoratz said if K, which is the height of the irregularities divided by the thickness of viscous sublayer, is less than 0.25, the boundary is smooth. If K by delta dash is greater than 6, the boundary is for sure rough. But if it lies in between 0.25 and 6, the boundary is transitional. In terms of roughness Reynolds number, so actually there is something called roughness Reynolds number that is dependent upon K, the height of the irregularities. So, in terms of roughness Reynolds number, if this Reynolds number is less than the 4, the boundary is smooth. If it is more than the 100, then the boundary is rough, and it is lies between 4 and 100, the boundary is transitional. So, either we can calculate it in terms of K by delta, where K is the height of the irregularities and lambda dash is the viscous sublayer, or more, it is more easy to calculate U star K by nu. If this is less than 4, it is smooth. If it is more than 100, then rough. Otherwise, in between, it is a transitional boundary. Now, we will solve one problem about this particular concept. So, the question is, a pipeline carrying water has average height of irregularities projecting from the surface of the boundary of the pipe as 0.15 millimeter. What type of boundary it is? We have to estimate the rough or smooth or transitional boundary. The shear stress at the pipe wall is 4.9 meters per Newton per meter square, and the kinematic viscosity is 0.01 Stokes. So, shear stress at the wall is given, right? So, we will be able to calculate U star from here, but okay, better that we go and start doing the problems as we have been doing. So, we have to write the things that it has been given to us. K is given as 0.15 millimeter. It is always a good habit to write it into SI unit, into 10 to the power minus 3 meter. tau naught is actually given here, 4.9 Newton per meter square. Okay, and nu is also given, 0.01 into 10 to the power minus 4 meter square per second. Therefore, we can simply calculate u square as under root tau naught by rho, as I told you, and this will come out to be under root 4.9 by 1000. So, it will come out to be 0.07 meters per second, very simple. So, best is to calculate the roughness Reynolds number, Re star, and that is given as u star k by nu. So, Re star is, u star is 0.07, k is 0.15 into 10 to the power minus 3, and nu is 0.01 into 10 to the power minus 4, and that comes to be 10.5. So, as Re star lies between 4 and 100, this implies that the boundary is transitional. Okay. So, just going back to that screen. So, what we have got is Re star is 10.5, implying transitional boundary. Okay. So, this is the place where we will end this lecture of ours today, and resume in the next lecture, and we will talk about turbulent flow in smooth pipes. So, I will see you in the next lecture. Thank you.